Section 8.2 of exponentials. Well, the first thing I need you to do is graph something that has a value A. And that to look of the I know that we all should be able to understand that this comes from exponential growth, right? Because the value of B, the growth factor, is larger than 1. So if you remember what exponential growth looks like, exponential growth looks something like that. Um, well, that negative A value actually takes the whole graph and flips it down across the x-axis so that, yes, you have a negative um, value for your y-intercept, but your graph is going to be almost a mirror. It's going to be a mirror image of that function just in that direction below the x-axis. So looks a lot like the exponential growth, just flipped over the x-axis. Um, so same thing here. You've got your exponential decay function because the growth factor is less than 1. So we remember what those things look like. And so we have -4 for our y-intercept, and we have a shape which is mirror imaging that shape on the other side of the x-axis. So that's what happens when you have a negative multiplier, and I'll just ask you for a sketch of those. So if you understand what the growth function looks like, then just flip it over the x-axis. You'll be fine. We are skipping example 6 or example 2, so don't need to worry about doing anything with example 2. We are moving to an example 3. We're going to talk about half-life. There are many substances which have what's called a half-life. For instance, there are certain radioactive drugs that need to be given to cancer patients, and they need to be administered in a fairly short amount of time because those drugs actually start to decay because once they're created, they start the process of decaying. So their potency is not as strong. So they need to be administered sometimes at different odd times. So these pharmacists have to be on call. But there are other substances, radioactive substances that we have, or even things that the scientists use carbon-14 to check dates of different things. And any substance that has this half-life property, you can use to find how long it's been or how much is left of a substance after a certain amount of time. So for instance, in a half-life question, the growth factor will always be 0.5. That's fairly easy, and you should always remember half-life and the substance remaining will be half as big as it used to be. Now, A is always the same for these story problems, right? That's the starting amount. So whatever substance we're dealing with, we'll start with a certain value. And you'll notice that the exponent is a fraction. And you'll notice that the denominator of the time factor, right, x represents time, the denominator will be the half-life period. That'll be the length of time it takes to become half of what it used to be. Sometimes those are hours, sometimes days, sometimes weeks, sometimes years. Depends on what substance we're dealing, or what kind of compound or substance you have. If you look at example 3, they talked about this substance called technetium 99M, which has a half-life of 6 hours. That means when it starts out at 100, so in this case they said they were starting out with 100 milligrams of the substance. So we know that the starting amount is 100, 0.5 is the growth factor, and x divided by the half-life period. So after 3 hours, or after 6 hours, I should say, this is going to be half of what it used to be. So it goes from 100 to 50. Now, yes, it's doing it gradually. It's not doing it instantaneously. But you can ask me other questions like, so not only do I have to write the equation, but maybe I have to figure out that after 25 hours, how much of that stuff is left. So let's see here. Use our handy dandy calculator. 100 times 0.5 raised to the, please make sure that you use parentheses around your fractional exponent, 25 over 6. Found out that there would be 5.57 milligrams of this stuff remaining. 5.57 milligrams. It's just over a day. 25 hours being just more than a day is 5.57 milligrams remaining. So some of these substances or compounds can reduce or be reduced in a short amount of time. Now, the next formula looks kind of nasty, but it's a compound interest formula, and it's an exponential model. No, you don't have to memorize this. I'll have it for you probably on the top of the quiz or something like that, or in the question you need it for. So we have the amount of money after t years. So that obviously means that t is the number of years. P is the principal, and that is the amount you start with, right? Starting amount. Well, that sounds familiar. We've talked about starting amounts before. R represents the interest rate as a decimal. If you mean 7%, don't you dare put 7 in there for R. If you think it's 7%, you make sure you understand that that means that R is 0.07. Change it to a decimal first. Okay, next, N. You see it twice in the formula. This is the part that's more confusing to some of you. It is the number of times compounded. Now, what does that mean? Well, compounding means that I can split up the interest into pieces and give you those pieces at different intervals. So, for instance, I could split up the interest and give it to you once a year, twice a year, split up the interest into smaller pieces, give each one of those pieces to you 4 times a year, or 12 times a year, or 52 times a year, or 365 times a year. In other words, now, I know that you don't understand or you see it thinking, why would you split up the interest? Well, the reason is, the more times you split it up, the more interest you're going to earn on top of the interest you've already been given. Albert Einstein said that compound interest is one of the most amazing things because you're getting money on top of money. So, what kind of values will we stick in there for n? Well, let's see here. If we say that we're compounding annually, that means n equals 1 time a year. If we're compounding quarterly, that means we're compounding 4 times a year. How about monthly? Weekly? Daily? So look at the words in the story problem to determine which value of n we're going to use. So let's see here. We're going to have to probably need to do an example of this. So let's see here. $1,000 is invested at 7% interest. Compounded quarterly. Okay, that means that the n value is 4. All right. Quarterly, that means n equals 4. You know, r equals 0.07. For 5 years. 5 years. How much money do you have? $1,000 times 1 plus 0.07 divided by 4 raised to the, please make sure you have parentheses around your exponent unless you already know what 4 times 5 is. 1,414.78. Now, let's suppose for fun, we invested $1 at an interest rate of 100%. So this is my investment, this is my interest rate, 100%. This is the equation for 1 year. Right, you can see right there the t value is 1. And then we could take a look at changing the compounding factor. Well, there was a guy who did this. I don't know if he was bored or what, but he just started increasing the value of n. And he looked at this function. And he noticed that as he continued to pick bigger values for x, which is no different than the value of n, that he started to get a value for y which was closer and closer and closer to one particular number. In other words, there was a horizontal asymptote to the graph. And that number that it got closer and closer and closer to was 2.718. But not only 2.718, it was also irrational. And you know, irrational numbers like pi, they keep going forever and ever, and they never stop and they never repeat. Well, they decided to name this number after the guy, Leonard Euler, that came up with it. And when they did that, they named it E. So E, which is programmed into all your scientific calculators, is 2.718. Now, if you recognize the number 2.718, pay attention to the door when you come in my room tomorrow where it says my name, and then read it. If 2.718 is E, read it, okay? And you'll probably get the joke. Well, okay, let's see here. Couple questions. Find E squared. Okay. E is actually, let's see, where is that? Okay. I see the e to the x button right here on my calculator. So, second e to the x, and it puts e to a power on there. I'm going to type 2 and just see what happens. E to the second power, 7.389 approximately. E to the fifth. Okay, I'm going to go up, go over and change that to a 5. 148.413. E to the negative first. Okay, so let's see here. That's negative 1. Oh, there's a number smaller than 1. Well, that makes sense because the negative exponent flipped the base over, so it had to be a number smaller than 1. So 0.368. E to the 0 is the number 1. Everybody knows that anything to the 0 power except 0 is actually equal to the number 1. Well, what does that graph look like? If E is 2.718, then this is almost the same thing as 2.718 to the x power. Well, what is that graph going to look like? Well, 2.718, is that larger than 1? Sure it is. So that means exponential growth. Now, what happens if you take this compound interest formula and you start raising n to a really big number? A really big number. Well, guess what this thing turns into? This thing turns into e to the r power. So you can see that my p stays in the equation, and you can see my t stays in the equation, but the part in the middle changed to e to the r. We call it the PERT formula, pe to the rt power. Now, the only time you're going to be using this is when you see this phrase, compounded continuously. As soon as you see that phrase, instead of compounded quarterly or annually or daily or weekly or monthly, if you see compounded continuously, automatically choose the PERT formula. Now, keep in mind that R does not involve adding 1. I made that note right here. Lots of kids like to add 1. Well, that means something completely different. R is still a decimal, unless, of course, the percentage that we're increasing is over 100%. If it's over 100%. Excuse me for yawning so many times. I'm sure some of you are yawning and swearing at me because I am yawning. Just a little bit tired these days. So let's see, example 5. We know in example 5 they talk about it being compounded continuously. You invest $1,050. You get an interest rate of 5.5%, which we know is an R value of 0.055 for 5 years. How much money would you have? Well, we know this is the PERT formula that we're dealing with because of the compounded continuously phrase. So we have 1,050 e to the 0.055 times 5 years. Let's use our calculators for this. 1,050 e to the 0.055 times 5. $1,382.36. And that's how difficult it is to figure out that formula, or putting values into that formula. A lot of things, if you're using your calculator on things, make sure that you use parentheses around your exponents. We'll talk in class.